Hello, everyone. Welcome to Physics 205, Physics and Movement Science. So today what I want to talk about is a very special case where we have one-dimensional motion, but we have constant acceleration. So it's constant accelerated motion. So what we're going to do is we're going to derive the equations of motion that we can apply to the situation where we have constant acceleration. And then we'll do several applied examples that involve constant accelerated motion. Okay, so to begin, remember that the average acceleration in the x, I'll call it ax av, is defined to be the change in velocity in the x direction divided by change in time. And I can write this as Vx final minus Vx initial divided by T final minus T initial. Or I could just leave it as delta T. Actually, let's just leave it as delta T. So I'll write this as Vx final minus Vx initial. And I'll leave the denominator as just the change in time, right? That time interval. Okay, so now if that average acceleration is constant, so if acceleration is constant, then that means that the average acceleration is simply going to be the acceleration, right? Which we can maybe give it another name. Maybe we'll call it A. So if the acceleration is constant, then that means ax av is simply equal to some constant, which I'm just going to call A. Okay, so A represents my constant acceleration. So then I can rewrite my equation now as A is equal to Vx final minus Vx initial over delta T. And then usually what I like to do, just to keep things a little simpler, is I'm going to just write the final velocity as Vx. And then the initial velocity, I'll write V naught x over delta T. Okay, so now let's solve this equation for V final, so for Vx. So how do I solve this equation for Vx? Well, first I need to multiply both sides by delta T. So I'll do A times delta T, and I'll do the same thing on the right side. So on the right-hand side, delta T's cancel, right? So now I have A delta T is equal to Vx minus V naught x. And then finally, I can add V naught x to both sides. So add V naught x to both sides. And then I'll rewrite this. So now I just have Vx now on the right-hand side, but I'll write it on the left-hand side because that's what we're going to be looking for basically is the final velocity. That's equal to the initial velocity, V naught x, plus a delta T. Okay, so that is like our first important equation where we have constant accelerated motion. If I know the final velocity, I know the initial velocity, and I know the time, and I want to solve for acceleration, I could use this equation. If I know three of the other variables, let's say I know initial velocity, acceleration, and delta T, I could solve for the final velocity. So if I know three out of these four variables, I can solve for the remaining variable. Okay, next. If A is constant, so if the acceleration is constant, which is the situation we're dealing with right now, then this is going to be true. So if A is constant, then it turns out that the average velocity, I'll just use a bar for average in this case, average velocity in the x direction is simply equal to the initial velocity plus the final velocity divided by 2. It's simply the average of the initial and final velocities. How can we see that? I can show you a little plot here. Let's say I plot velocity versus time. So I have velocity, say meters per second on the y-axis, time on the x-axis in seconds. It's constant acceleration, right? So we know that our velocity versus time graph should be linear, right? If it's constant acceleration, the acceleration would be the slope. If it's constant, it has to be the same slope. So this is just going to be a linear function here, right? So it's going to be a line, this graph. So let's say it looks like that, just some line. And assume that this is the initial velocity, and let's say this is the final velocity. So you might be able to kind of see this, right? If I want the average velocity over this time interval, so the time interval would be this interval right here, delta t. You can almost guess, right? The average velocity, and it's increasing here, is going to be like right in the middle. So that average right there is really the average of the initial and final velocities because it's right in the middle. But that's only true because this function is linear here, right? If it had some other weird shape, then the average wouldn't necessarily be the average of these two. It wouldn't necessarily be right in the middle. But if you have constant acceleration, then that is true. So this is going to be true, where that average is simply the average of the initial and final velocities. Okay. By definition, another way, right, of writing the average velocity, so say by definition, the average velocity is equal to the change in position, right, the displacement, divided by the change in time. Or I could rearrange this. I could write this as the displacement is equal to the average velocity times time times delta t. Right? I basically just multiplied both sides. Here, I'll do the algebra out over here. I basically multiplied both sides by delta t. Right, whatever I do to one side, do the other side, a little bit of algebra, I can cancel the delta t's here. So I have delta x is equal to the av x times delta t. And I just wrote the delta x on the left-hand side. Okay, now let's substitute in what we just wrote for our average velocity. Remember, another way of writing this is I can say this is v naught x plus vx divided by 2 times delta t. Right, so this term right here is my average velocity in the x direction. And then I'm going to plug in for vx here, I'm going to plug in what I just found earlier, that previous equation. Remember, vx is equal to v naught x plus a delta t. So if I substitute that in, I'm going to have this. I'm going to have delta x is equal to v naught x plus, and then this becomes v naught x plus a delta t. That's all divided by 2 times delta t. And then I can simplify this a little bit, right? So I have, it looks like I have 2 v naught x's, right? These are like terms, like 1 v naught x plus 1 v naught x is going to be 2 v naught x. So I'll write that as 2 v naught x plus a delta t over 2. I can distribute in this delta t. Actually, let me cancel the 2's first. So I'll write this as, this is simply going to be v naught x, right? Plus, and then 1/2 a delta t. That's all times delta t. And then I can distribute in the delta t. So the final equation here is going to be delta x, the displacement, is going to be v naught x delta t plus 1/2 a delta t, and I have two of them, so that's going to be squared. I'll write like this, squared. Okay, so that actually is our second really important equation that we can use when we have constant accelerated motion, right? So when the a here is constant, then I can use this equation to solve for some of the variables. Now, usually this is used when you want to find delta x, right? If you know the initial velocity in the x direction, you know the change in time, and you know the acceleration. If you know those three variables, then we can find delta x. But you could find one of these other variables. Let's say we know delta x, v naught x, and a, we could find delta t, right? By rearranging this equation. So it's our second really important equation for constant accelerated motion. Okay, there's one more equation that we use all the time. And I'll give you guys a sheet later that summarizes all these equations. So now I want to start with Vx equals v naught x plus a delta t. So I'll start with that equation, the first one that we derived. And I'm going to solve for delta t. So how do I do that? Well, let's just do it out here. So algebraically, how would you solve for delta t? Well, first, I need to subtract this v naught x, right? From this side to get a 0 there, but whatever I do to one side, do the other side. So this is going to be vx minus v naught x is equal to a delta t. And again, if I want delta t by itself, I need to divide both sides by what is being multiplied by is a, right? So I have a 1 delta t. But again, whatever I do to one side, I have to do the other side. So this is going to simplify. So the a's cancel here. So delta t here is simply going to be v final, right, minus v initial over a. Now I'm going to plug this in to this equation. So remember earlier we had delta x is equal to v av times delta t. But I can write that as delta x is equal to v naught x plus vx over 2 times delta t. And I'm going to factor out that 1/2. I'll just bring it out front. So I have 1/2 v naught x plus vx times delta t. And now I'm going to substitute in what I just found for delta t here. I'm going to plug that in for here. Okay, so then that'll be delta x is equal to 1/2 v naught x plus vx times vx minus v naught x over a. And then I'm going to have to work this out. So this is going to be I guess I can bring out that a, right? So I have 1 over 2a. And then I'm going to have to FOIL that numerator. So if I FOIL that, I'm going to get, let's see, I have 1 over 2a. Then if I do, right, first times first, I'm going to get v naught x times vx. Then outer terms, I'm going to get minus v naught x squared. Then inner terms, I'm going to get plus vx squared. And then last, I'm going to get minus vx v naught x. And notice here that I have positive v naught x vx, and I have minus v naught x vx, right? It doesn't matter what order you multiply in. So those are the same. They cancel. One's positive, one's negative. They cancel. So this is really I have left. I have delta x. Oops, let me do this back in. I have delta x is equal to vx squared. I'm going to write that term first, minus v naught x squared over 2a. And then I can multiply both sides by 2a. So the 2a's cancel, right? And finally, usually it's written, you solve it for vx squared. So I'll just do that. I'll write it as vx squared is equal to, I'm going to bring this term to the other side. So I'll add it to both sides. So I'm going to get v naught x squared. And then I have a plus 2a delta x. So this constant acceleration equation is nice because it doesn't involve the time, right? So if your information just involves vx, v naught x, a, and delta x, doesn't involve the time, then you could use this equation. So this is like our third important equation for constant accelerated motion. Now I have all of these summarized. So this is on Brightspace. You can download this if I haven't already handed it out in class. Let me just show you this. Okay, so here's a sheet where I basically summarize all those equations. So for the horizontal motion, right, remember we're going to call that the x direction. One of the equations is simply that delta x is equal to the average velocity in the x direction times delta t. And this just comes from that definition, right? The average velocity is delta x divided by delta t. So I just rearranged it. However, we know if we have constant acceleration, then the average velocity is simply equal to the average of the initial and final velocity. So v naught x plus vx divided by 2. And then these are the three equations that we derived. Vx is v naught x plus ax delta t. We have the one for the displacement. Delta x is v naught x delta t plus 1/2 ax delta t squared. And finally, the one that doesn't involve the time. Vx squared equals v naught x squared plus 2ax delta x. I'm putting in a subscript on the a now to represent it's just in the x direction. Okay, vertical motion is exactly the same thing, except now instead of x here, all these subscript x's, I have y's. That's the only difference. Instead of x's, I have y's. They're exactly the same 5 equations. Okay. And then later I'll talk about this in a little bit. But what if we have, so this is sort of like the special case. Now, let's say we're talking about vertical motion with constant acceleration, but we're talking about free rise, free fall motion, which is motion just under the influence of gravity. Then it turns out that the acceleration in the y direction, so all these AYs here, you could replace by putting in negative g, negative 9.8 meters per second squared, minus the acceleration due to gravity. So these AYs, they're constant, but they actually become negative 9.8. So same exact equations again as my vertical direction, except instead of AY, I have negative G's here for all my AYs. Okay, so I think you'll find this sheet right here to be really helpful, these kinematic equation sheets here. You can refer to it often. You can use this on your homeworks, on your exams, on your projects. Okay, let me go back to the iPad and we'll do a bunch of examples now. Okay, here's the first example. You're told that a runner traveling with an initial velocity of 2 meters per second accelerates at a constant rate. So that's how we know it's constant acceleration problem, right? Constant rate of 1.2 meters per second squared for a time of 2 seconds. And we want to know what is his velocity at the end of this time and what distance or what displacement, right, does the runner cover during this process? Okay, so first thing I would do is write down, what do we know? Well, we know that the initial velocity is 2, right? So we can write v naught x is equal to 2.0 meters per second. That's known. We also know the acceleration, I'll call it AX in this case, because we're in the X direction, is 1.2 meters per second squared. And we know the time, right? So we know that the time interval, delta t, was equal to 2 seconds. And what are we looking for? Well, in part A, we're looking for the velocity at the end of this time interval. So we're looking for Vx, right? The final velocity. That we don't know. So the way to think about this, if you go to your kinematic equation sheets, is there any equation that we have where we know 3 of the variables and the only unknown, there's only one unknown variable, which would be the Vx? And if you look carefully, you'll see that this equation, the first one that we derived, Vx is equal to V naught x plus Ax delta t, that will work, right? Because we know the initial velocity in the x direction, we know the acceleration, we know the time, we can find Vx. The one that you're looking for obviously has to appear in the equation too, right? Because that's the one we want to solve for. So it's just a straightforward application of that equation. Okay, so now that I know this, let me just plug in these values. So this is going to be 2.0 plus 1.2 times 2 seconds. And then if you work this out, so plug that into your calculator, be careful with order of operations. You should get 4.4 meters per second. So that's going to be the final velocity, 4.4 meters per second. Okay, and then part B wants to know the distance traveled, which is basically the displacement, right? Because this is one-dimensional motion. So again, based on what we know and what we're looking for, now we don't know delta x. We're looking for delta x. Now that I know Vx, I could actually use more than one equation, but probably the easiest one to use is that second equation that we derived. So I'm going to use that equation. So delta x is equal to V naught x delta t plus 1/2 Ax delta t squared. And again, in this case, I don't even have to rearrange anything. I can just plug in, right? So this is going to be 2.0 times the time, which is 2 seconds, plus 1/2 times 1.2 times 2 squared. If you work that out, you're going to find that you're going to get 6.4 meters. Okay, so we know the final velocity at the end of the time interval, and we know the displacement, how far the runner went, right, during that time interval. Okay, another example. You're told a car moving with an initial velocity of 30 meters per second. Actually, let me start writing down what we know. So we know the initial velocity is 30 meters per second, slows down at a constant rate of -3 meters per second squared. So that's the acceleration, right? And it's negative because they're moving to the right and slowing down. So AX is going to be -3 meters per second squared. And we want to know what is the car's velocity after 3 seconds of deceleration? What distance does the car travel in 3 seconds? And then how long does it take the car to come to rest? Okay, so part A. We want to know the velocity, so the final velocity, which we don't know, but we are given now the time. What is the time? It's going to be delta t is going to be 3 seconds. Right? What is the final velocity after 3 seconds of deceleration? Okay, so again, if we know the initial velocity in x direction, we know the acceleration, we know the delta t, and we're looking for the final velocity, what equation can we use? We can use that first equation that we derived again. So Vx is V naught x plus Ax delta t. So Vx is going to be 30 plus, now be careful, remember A is -3 times 3. So if you work that out, that's what, 30 minus 9, right? So that's going to be 21 meters per second. That would be the velocity of the car after 3 seconds, right? It's slowing down because you have this negative acceleration. It was moving initially at 30, now it's moving at 21 meters per second. Okay, what distance does the car travel in 3 seconds? So now we're looking for delta x, right? The displacement. Well, again, we could just use this equation that we derived, the second one that we derived, v naught x delta t plus 1/2 ax delta t squared, because we know the time, we know the initial velocity, we know the acceleration. So it's a matter of just plugging in here. So v naught x is what, 30? The time was 3. The acceleration was -3. And then the time was 3, but I need to square that. Okay, so if you work this out, right, this is going to be, this term right here will be 90. And then this is what, like minus 27 halves, I guess, right? Negative. So you're going to get a displacement, if you plug this into your calculator, of 76.5 meters. So that's how far it's gone over that 3 seconds as it's slowing down. Okay, and then the last question was, how long does it take for the car to come to rest? Okay, so what does it mean for the car to come to rest? Well, it means that its final velocity, so I'll say when car comes to a rest, it means that its final velocity is going to be 0, right? 0 meters per second. And we're looking for the delta t, the time interval, when the car has come to a rest, when its final velocity is 0. We still know the initial velocity is 30. We still know the acceleration. So it turns out we could just use this equation again, right? Vx equals v naught x plus ax delta t, except now my unknown is my delta t, right? I know everything else. I know my final velocity should be 0. I know my initial, I know my acceleration. So now I want to solve this for delta t. Now, there's a couple ways you could do this. You could plug in numbers and then solve for delta t. It's better if you solve it algebraically. But I'll leave it up to you how you guys want to do this. I'm going to solve it algebraically right now. So to get delta t by itself, I need to subtract v naught x on both sides. So vx minus v naught x equals ax delta t. And then finally, I have to divide both sides by ax. Right, ax cancels. So now I have delta t is equal to vx minus v naught x over ax. And then I can plug in. Remember, my final velocity was 0. My initial velocity was 30. And then my acceleration was -3. Actually, this is nice. This is a good way of checking, right? So I have negative, so 0 minus 30 is -30, divided by -3 is +10. And it makes sense. The time had better be positive, right? The answer better be positive. Wouldn't make sense if you got a negative time interval. So it makes sense that we got, a positive answer, in this case, 10 seconds. So in 10 seconds, this car comes to rest. Okay. It is much better to rearrange algebraically the equation and then plug in at the end like we did here. Although I do understand sometimes students really dislike doing that. They're afraid sometimes they might make some algebraic mistakes. Then you could plug in the values here and just solve for delta t, okay? But you should get in the habit of doing this because it actually is better to do it this way, where you solve it algebraically, then plug in. Okay, another example. So in this case, you're told that a park ranger driving on a backcountry road suddenly sees a deer frozen in the headlights. The ranger, who is driving at 11.4 meters per second, okay, so that's his initial velocity. So let me write that down here. So v naught x equals 11.4 meters per second. Immediately applies the brakes and slows down with an acceleration. So we know the acceleration as well, ax is -3.80 meters per second squared. Okay, and that's all we're given, right? We're given the initial velocity, given the acceleration. Then it says, if the deer is 20 meters from the ranger's vehicle when the brakes are applied, how close does the ranger come to hitting the deer? Okay. So what else do we know? Well, the way it's asking this question is we're assuming the ranger's vehicle comes to a stop, right? Which would mean its final velocity is equal to 0, right? If it comes to a stop. And we want to travel, we want to figure out, we want to calculate how far it's traveled, right? We want to figure out its displacement, delta x. And hopefully it's less than 20. If it's less than 20, then we know that the deer did not get hit, right? So do we have an equation that allows us to solve for the unknown delta x, and it also has v naught x, vx, and ax, has the other information that we need? Yes, we do. It's the one that we haven't used yet, right? It's this equation. So this is really part A. It's this equation here, right? Vx squared equals v initial x squared plus 2ax delta x. Okay, so I can solve that for delta x. So I'm gonna do that algebraically first. I'm gonna subtract v naught x from both sides, or sorry, v naught x squared, right, from both sides. And then I'll divide. So right now I have vx squared minus v naught x squared equals 2ax delta x. Then I want to solve for delta x. I'm going to divide both sides by 2ax. So this will cancel, and I'm going to get, I'll write it over here, delta x is equal to vx squared minus v naught x squared over 2ax. Okay, so now let's plug in our values. Let's calculate what that displacement is. So we know the final velocity is 0, right? They come to a rest. The initial velocity was 11.4. I got to square that. And divide by 2 times the acceleration, which is negative 3.8. Again, this is good, right? The negatives are going to cancel here. So I'm going to get a positive displacement, which makes sense. I'm moving to the right. And if you work this out, you're going to find that your displacement is 17.1 meters. So that's how far it took before they stopped, 17.1 meters. Okay, so now if we want to figure out how far, I guess this question's asking how far or how close does the ranger come to hitting the deer? Then if I take, remember the deer was 20 meters away. If I subtract 17.1, what's that? I'm going to get 2.9 meters. That's the distance between the car and the deer, right? When the car stops. Distance between car and deer, right? When the car stops. Okay, so we answered part A. Then let's see, what's the other question? How much time? Okay, so how much time was needed for the ranger's vehicle to stop? So for part B, we don't know the time, right? We're looking for delta t. So in this case, I guess we could just use this equation. Vx is v naught x plus ax delta t. Because we know the final velocity, again, it was 0. We know the initial velocity, we know the acceleration. We could solve that for delta t. So I'm going to solve this for delta t. So I have vx minus v naught x equals ax delta t. I'll divide by ax. Again, if you really don't want to do this, you could just plug in your values immediately. But I highly recommend that you do it this way. So delta t is going to be vx minus v naught x over ax. And now if I plug in, so final velocity is 0. Initial velocity was 11.4. The acceleration is negative 3.8. And then if you work this out, you're going to get an answer of 3 seconds. Positive 3, which makes sense again, right? It has to be a positive value if it's a time interval. So the car, this ranger's vehicle stops in 3 seconds. Okay, another example. A car starts from rest and travels for 5 seconds with uniform acceleration of 1.5 meters per second squared. The driver then applies the brakes, causing a uniform acceleration of -2 meters per second squared. If the brakes are applied for 3 seconds, we want to know a couple things. How fast, so we're looking for like the velocity the car is going at the end of the braking period, and how far has the car gone. Okay, so in this case, we have to basically solve this in 2 steps. Okay, so first we'll find out like how um, we'll find out the velocity and how far the car has traveled after just the first 5 seconds, right? When it has that positive acceleration. And then we can find, um, I guess we could solve it again if we know that velocity now, which becomes the initial velocity for the second part of the problem. Okay. So here, I'll write this down carefully. So we want to solve this in 2 steps. Kind of have to break this problem up, right? So the first thing we're going to do is find the velocity of the car and the distance traveled after traveling 5 seconds. Okay, so if you want, you can even draw a picture here, right? So the car is at rest. It's going to have an acceleration to the right. So AX is going to be 1.5 meters per second squared. And it's going to travel for 5 seconds. So we know delta T is 5 seconds. And we're looking for this final velocity. And we're going to also look for how far it's traveling. Okay. Actually, let me call this like I'm gonna call this like Vx1 and delta x1 since it's just the first part of the problem. Because then later what's gonna happen, I'll do this in red now. Now you can think of it as like starting with this initial velocity, and now it's gonna have an acceleration that is negative. It's gonna decelerate. So now the acceleration, this is like AX2 now, is going to be -2 meters per second squared. And it's applied for 3 seconds. And we want to know where that car ends up. Like what is its total displacement and what is its speed right after that second part. But we need to do this first part first. Let's figure out what's going on right after 5 seconds. Okay, so let's see. I know the acceleration. I know the time. I know the initial velocity. In this case was 0, right? Because it started at rest. So to find that final velocity, Vx1, it's simply going to be an initial velocity plus AX delta T, right? I can use that equation. So this is going to be 0 plus 1.5 times 5, which is going to be 7.5 meters per second. And then to find that displacement, I can use this equation, right? V naught x times delta t plus 1/2 ax delta t squared. Because I have all, again, I have all the information. So this will be 0 times 5 plus 1/2 times 1.5 times 5 squared. And that turns out to be 18.75, right? Or like, let's say 18.8 meters. I'll just leave it as 18.75. We can round later if we need to. Okay, So that's after the first 5 seconds. Now, the second part, you can think of this as the following for part 2. Now, the car has an initial velocity of the velocity that we just found, right? Of the 7.5. Because at this point right here, it's traveling at 7.5. So now we're just dealing with the second part, right? This part right here, where it has this velocity of 7.5, and now it's decelerating for 3 seconds. Okay, so I can certainly find this final velocity here, whatever it may be, because I know the initial velocity now, which is the one we just found, 7.5. I know the acceleration is -2, and I know the time, right? So I can say, yeah, let me write this out carefully. I'll say solve the second part with a beginning velocity. I'll say an initial velocity of 7.5 now meters per second, and acceleration of -2 now, right? Meters per second squared, and a time of 3 seconds. Okay, so that velocity now at the end must be equal to the initial velocity plus ax delta t. So now I can plug in. Now the initial is 7.5. The acceleration was -2, and it was for 3 seconds, right? And if you worked it out, that's like 7.5 minus 6. This is going to be 1.5 meters per second. Okay, we could also figure out how far the car went just for that second part. So since I called the first part delta x1, let me call this delta x2. And then later I can add those together if I want the total displacement, right? Because I think they're asking for the total displacement ultimately, so I can add those together. So how do we find delta x2? Well, again, we know a bunch of information. We know the initial velocity, right? When it was at the 5-second mark. We know the acceleration. We know the time that it travels for that second part where it's just decelerating. So we can find that acceleration, or we can find the displacement just for that second part. So delta x2 here, it's going to be that standard equation, v naught x delta t plus 1/2 ax delta t squared. So this is going to be 7.5 times 3 plus 1/2 minus 2 times 3 squared. And that turns out to be 13.5 meters. Okay, so we're not quite done yet, right? We actually have the answer to part A. Remember, part A was how fast is the car going at the end of the braking period? Well, that's this value right here, right? That is the 7.5 meters per second. And then part B was how far did the car go total? So to figure that out, we need to add our delta x1 plus delta x2. Call that whole thing maybe delta x, and that will give us the total distance that the car traveled. Okay, so one more step here. I just have to find the total distance, delta x, which is the sum of delta x1, that first displacement, plus the second displacement. And remember, this was like 18.75 plus, and the second displacement was 13.5. So if you add those together, you're going to get 32.25 meters. And I should probably round it to like 3 sig figs. So I'll do 32.3 meters. So that would be the total displacement of this car. So this one was a little trickier because we had to split it up into pieces, right? There was one piece where it was accelerating for a particular time, and then the second piece, it had a negative acceleration, right? It was decelerating for a particular time. So we really had to kind of split it up to solve the entire problem. Okay, let's talk a little bit about free rise, free fall motion. Now, so let me write this down. So free rise, free fall motion. So basically, this is motion that occurs when an object is near the Earth's surface, right? So it's only acted on by gravity. And so let me again write out this definition here. Assuming no air resistance, that makes it much more challenging if we have air resistance. I know in reality, sometimes we do have to include air resistance, but for most of our examples, we're going to assume no air resistance. An object that rises or falls under the influence of gravity and we should really say near the Earth's surface. Okay, this is just if it's near the Earth's surface. If you're way up, a mountain's not going to mean much, but if you were like way up in the atmosphere, this would not apply. So we're assuming like right near the Earth's surface. So if this is true, assuming no air resistance, an object that rises or falls under the influence of gravity has an acceleration of AY, right? Remember, because we're talking about the vertical direction now, is equal to minus G. And this G here is the acceleration due to gravity. And its value, its magnitude is 9.8 meters per second squared. So in our case, right, our AY is going to equal negative 9.8 meters per second squared. So if we're given some particular problem where an object is, say, thrown up, right, or is released from rest and falls, right, just under the influence of gravity, then that means the acceleration in the y direction, we can just plug in negative 9.8. Okay, so that's why if you look at those kinematic equations, right, if you go to my sheet there, if it's free rise for fall motion, then all of these equations in the y direction are changed slightly so that instead of doing plus AYT, that AY is minus G, right, delta T. So it'd be like the first equation would be Vy equals V naught Y minus G delta T instead of plus AY delta T, it's just minus G delta T. Because I'm replacing AY with minus G. And remember, G is 9.8, right? So really just replacing AY with negative 9.8 when you say not minus G. So the second equation, delta y, this is the displacement in the y direction, is going to be v naught y delta t, and then it's minus 1/2 g delta t squared. And then finally, the last equation would be vy squared equals v initial y squared minus 2g delta y. Okay, so they're exactly the same equations, except ay is replaced by minus g. And again, you can look at that sheet that I gave to you guys, so you don't have to memorize all these. Okay, let's do some examples with free rise, free fall motion, and then we'll do a couple more general examples at the end, and then that'll be it for this video. All right, so in this case, you're told a ball is thrown vertically upward with a speed of 25.0 meters per second. And we want to know how high does it rise? We want to know how long does it take to reach its highest point? We want to know how long it takes the ball to reach the ground. And then what is the velocity of the ball right before it hits the ground, right? So we need to know all this information. So, okay, what do we know in this problem? Well, first thing, I know that my initial velocity in the y direction is 25.0, right? Because it's thrown up, so it's positive, and we know that initial velocity is 25. That's when that's the speed that it leaves the person's hand at, right? So the velocity is positive 25.0 meters per second. We also know that ay is minus g. So ay is minus g, but it's already built into the equation. So really all we need to know is g is 9.8, right? The negative is already built into. So g is negative 9.8. Sorry, g is 9.8 meters per second squared. The negative is already built into the equation for you. Okay, how long does it take to rise to reach the peak? Well, we're looking for delta t, right? We don't know delta t. That's what we're trying to figure out. But there is something else that we do know. At the peak, what is the velocity of the ball? Well, it must be 0, right? Just for an instant, but right at the very highest point, its velocity in the y direction. So v final y is going to be 0. So do we have an equation that involves all these variables where the only unknown is delta t? Yeah. We could use, let's see. I guess we could use, oh, you know what? I made a mistake here. I'm starting to answer the second question, right? Let's do the first, so let's do part A first. We want to know how high does it rise, right? That's the first question. So really I'm looking for delta y here. Right, the next part B, we want to know the time, but for now let's just do it. We'll just do part A. So the question is, do we have an equation that involves all these variables and the only unknown is delta y? Yeah, that we also do, right? This equation right here, if we use vy squared equals v initial y squared minus 2g delta y. That I can solve for delta y, and I already know all the other variables, right? I know the final velocity should be 0. I know the initial velocity is 25, and I know g, of course, is 9.8. So I'm going to solve this now for delta y. So I'll subtract v naught y from both sides, and then I'm going to divide by minus 2g. Okay, so this will cancel, and I'll finish over here. I'm going to have delta y is equal to vy squared minus v naught y squared divided by minus 2g. Okay, so now let me plug in. Final velocity is 0. Initial was 25. And then g, remember, is just 9.8, right? Don't put a double negative there. It's just 9.8. We already have the negative built into the equations. And if you work this out, you're going to find that that displacement is 31.9 meters. So that's how high the ball rises. Okay, to figure out the time to reach the highest point, I kind of was jumping the gun, right? Now I want to actually find delta t, the time that it takes to reach the final height. And again, I know that that velocity, the final velocity at the highest point, is going to be 0 because it's at rest just for an instant, right? The ball is like instantaneously at 0 velocity. So now if I look at my equations, well, I could use this one, right? I know Vy equals V naught y minus G delta t. And I could solve that for delta t. So subtract V naught y from both sides. So I'm going to get Vy minus V naught y is equal to minus G delta t. And then divide by minus G. So I'll finish it over here. So I have delta t is equal to Vy minus V naught y divided by minus G. And if I plug in, I'm going to have 0 minus 25 divided by negative 9.8. And that gives me 2.55 seconds. Okay, so 2.55 seconds. All right, what about part C? So let's see, what is C asking? How long does it take the ball to reach the ground? Okay, so we're looking for the time that it takes the ball to leave the person's hand, rise to the peak, and come back down to the person's hand again, right? One way of doing this is the following. I could say, right, if it leaves a person's hand, rises to a peak, and then comes back down again, since the final and initial positions are exactly the same, that means the delta y must be 0, right? Remember, delta y is like y final minus y initial. Well, that's going to be 0, right? Because they end up at the same spot. Now, is there an equation that, and we're looking for the time it takes for that whole thing to occur, right? To rise to the peak and come back down. Is there an equation that the only unknown is the time that we can solve for and we know all the other variables? Yeah, if you look closely at this equation, we actually know everything in this case, right? In this case, I'm just going to plug in values. So I know delta y is 0. V initial was what, 25. I don't know delta t. And then I do know G is 9.8 delta t squared. Okay, so then, and I guess 1/2 9.8, I could rewrite it, was that 4.9? So I could write this as 4.9. Delta t squared. And notice here, I could factor out a delta t from that equation. And I'm left with 25 minus 4.9 delta t. And since that product is equal to 0, then remember from algebra, I could either say that delta t is 0, or this term is equal to 0. Well, the delta t is 0. That doesn't help us, right? That just says it takes 0 time because the ball hasn't even left the person's hand yet, right? It's at the final position and the initial position in 0 time. That's true. But we want the second solution here. When we set 25 minus 4.9 delta t equal to 0, that's the solution that we want. We want that time. So if I solve this now, right, I could subtract 25 from both sides. So I have negative 4.9 delta t is equal to negative 25. And if I divide by negative 4.9, I'm going to find that delta t is equal to 5.1. Do another sig fig, 5.10 seconds. So that's the total time that it takes the ball to rise to the peak and come back down, okay? Now notice here, earlier we found that the time just to reach the peak was 2.55 seconds. And now we just found that the total time to go from the hand to the peak and back down to the hand again is 5.10 seconds. But notice that 5.10 is equal to twice 2.55. So as long as there's no air resistance, you can assume that there is a symmetry here. The time it takes to go up is equal to the time it takes to come down, okay? So if you understood that there was a symmetry, once you found this answer, the time it takes to reach the peak, you could have just doubled it and you would have known the answer, the total time that it takes. But that's only because there's no air resistance that has this symmetry. If there is air resistance, this is not true. It's not double the time. It's a little more complicated than that, okay? So you can either solve it directly like we did, or you could just say it's double the time that it takes to go up. Okay, and then the last question, I think I'm gonna have to do it over here. Need some room here. Is what is the time? Let's look at the question again. Oh, no, what is the velocity of the ball right before it hits the ground? Okay, well, we know the time it takes now to go leave the person's hand, go up to the peak and come back down. That was like 5.10 seconds. And we want to know the velocity right before it hits the ground. All right, so again, what do we know here for part D? We know the initial velocity, that was the same, right? That's going to be 25. We know the total time now that was in the air, like the time of flight, the time to go all the way up and come down was 5.10 seconds. Of course, we know G is 9.8, and we want to find the final velocity, Vy. So I can just plug directly into this equation. Vy equals V naught y minus G delta t. So if you do this, you're going to have 25 minus 9.8 times 5.10. And if you work this out, you're going to get Vy is negative 25 meters per second. Okay, what does the negative tell us? Well, the negative tells us that the ball is moving down, which makes sense, right? Because initially the ball was moving up. Here, let me draw a picture. Let's say it leaves the person's hand with this velocity. Remember, it was like 25. And then the velocity is going to get less, 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 until at the very peak, just for an instant, it has a velocity of 0. And then it's going to start falling. The velocity is going to be negative, more negative, more negative, more negative. And then right before it hits the person's hand, it'll be negative because it's going downward, but it has the same magnitude as when it left the person's hand. So it's going to be negative 25 meters per second. Again, that's due to the symmetry of the problem here. So basically the speeds are the same, right? Remember, speed doesn't care about direction. So the speed of the ball when it left the person's hand is 25, and the speed right before it hits the person's hand is also 25. But the velocities are opposite of each other, right? The initial velocity is positive 25. The final velocity is negative 25 meters per second. Okay. Another example. A ball is thrown vertically upward and caught by the thrower after 2 seconds, right? So 2 seconds is the entire time, the time of flight, the entire time that the ball was in the air. Find the initial velocity of the ball, and then also find the maximum height that the ball reaches. Okay, so we're looking, okay, what do we know? We know that the total time delta t is 2 seconds. And if it's caught by the thrower, so it leaves the thrower's hand and it's caught, that means that the change in y is going to be 0, right? Because again, remember, this is final position minus initial position in the y direction. That's going to be 0. And we're looking for v naught y. And of course, we know g is 9.8. So do we have an equation that contains all these variables except v naught y? Yeah, we could use this one, right? We know that delta y is equal to v naught y delta t minus 1/2 g delta t squared. Right? So the only unknown here is v naught y. We know all the other variables. I could solve this for, here, I'll just solve it algebraically for v naught y. So I'm going to add 1/2 g delta t squared to both sides. So I have delta y plus 1/2 g delta t squared is equal to v naught y delta t squared there. And then I need to divide, I guess, by delta t. So then I'm going to get, so delta t's cancel here. I'm going to get v naught y is equal to delta y plus 1/2 g delta t squared divided by delta t. And then if we plug in, so the delta y is 0. G is 9.8. The total time was 2. And then delta t again is 2. So then if you solve that, you should find that v naught y, the initial velocity that the ball was thrown at, is 9.8 meters per second, right? It's just a velocity. Just even though it has the same value as g, it's not related to g in this case. It's 9.8 meters per second. Okay, so that's the initial velocity the ball was thrown at, right? In order for it to leave the person's hand and come back down in a time of 2 seconds. Now, how do we find the maximum height that the ball reaches? Well, one way of doing this is we could just use symmetry, right? If we know that the total time that the ball was in the air from when it leaves the person's hand to when it hits the person's hand again is 2 seconds, that must mean that the time to reach the max height, just by using symmetry, right? We're assuming there's no air resistance or anything, must be 1 second, right? It must be half of the total time. So it must be 1 second. So now that we know the initial velocity, we know the time to reach height, we could just use this equation, right? We could say delta y is equal to v naught y, which we know now. Delta t is like 1 second now, right, to reach the max height, minus 1/2 g delta t squared. So if I plug into that equation, I'm going to get 9.8 times 1 minus 1/2, 9.8 times 1 squared. And that turns out to be like 4.9 meters. So that would be the maximum height that it reaches. Okay. If you didn't want to use symmetry, the other way you could figure out the time that it took, because really to answer this question, we needed to know this, right? The time it took just to get to the peak, to the max height. And we found it by symmetry. If you didn't want to use symmetry, you could also use this. You could use the fact that the final velocity in the y is equal to initial velocity in the y minus g delta t. And we know that the final velocity in the y when it reaches max height is 0. The initial we just found was 9.8. And if I solve this for delta t now, right, by subtracting 9.8 from both sides, so I'm going to have minus 9.8 is equal to minus 9.8 times delta t, divide by minus 9.8. Well, what's that? Well, that's going to be delta t is equal to, this is just equal to 1, right? Is equal to 1 second. So you could have found it that way first and then plugged in, but ultimately you would have to use this equation. We just happen to solve the time just to reach maximum height just by using symmetry. Okay, but either way will work. Okay, a couple more examples and then that'll be it for this video. So in this case, this is kind of a long-winded example here, although there's actually not a ton of work to do for this example, just happens to be a long-winded question. It says, it is the final seconds of an ice hockey game between the Flyers and the Bruins. The Bruins are down by 1 point. With 20 seconds left in the game, the Bruins pull the goalie and have him play as forward and attempt to tie the game. The Flyers successfully defend their goal for 9 seconds. With only 1.25 seconds remaining on the clock, a Flyer shoots the puck on the ice past the skates and sticks of the other players and towards the Bruins goal. The puck is 37 meters from the goal when it leaves the stick with an initial horizontal velocity of 30 meters per second. The shot is perfectly directed toward the empty goal, but the ice slows the puck down at a constant rate of 0.5 meters per second squared as it slides towards the goal. None of the Bruins can stop the puck before it reaches the goal. So the question is, do the Flyers win do they win the game by 1 point or 2 points? Do they actually score or not? And the way that we're going to solve this is we have to basically figure out how far the puck travels in 1.25 seconds, right? A lot of this information is redundant information. You don't need to know this. Like 20 seconds left in the game. They successfully defend their goal for 9 seconds. We don't need to know that, but this is important, right? There's only 1.25 seconds remaining when the Flyer shoots the puck. We know the puck is 37 meters from the goal, and we know that the velocity of the puck is 30 meters a second, and we know the acceleration, since it's slowing, it says slows down at a constant rate of 0.5. That means the acceleration is negative 0.5 meters a second squared. So if we figure out the displacement of the puck in this 1.25 seconds, and it's greater than 37 meters, then we know that the goal was scored, right? If it's less than 37 meters, then we know that the game ended before the puck reached the goal. Okay, so that's basically how we're going to answer that first part. And then the second part is so if it did cross the line, so we kind of have to answer the first part first, then what was the velocity of the puck as it crossed the goal line, assuming that it did score? Okay, so let's see if it scored at all. Let's answer the first part. Well, I know a bunch of things here, right? I know that my initial velocity is 30 meters per second. I know that my acceleration is negative 0.50 meters per second squared. And I know that the time, at least the time that we had on the clock, was 1.25 seconds, right? And I want to figure out the displacement. I want to figure out how far the puck went. If it's greater than 37, then I know that it scored. If it's less than 37, it didn't score. By the way, the other way that you could do this problem is you could assume that the displacement is 37 meters, and you could solve for the time, delta t, and if that is less than 1.25 seconds, then it must have scored, right? So you could solve this a couple of different ways, okay? So let's see, if we do it this way, okay, actually, I'm going to draw a picture as well here. So let's say this is my initial velocity of the puck. The acceleration was negative, right? And it's going to be negative 0.50, just due to the puck and its surface, which is the ice, so there's some friction there, so it's slowing it down. We'll definitely talk about friction when we get into Newton's laws. And we want to know how far it travels, so it's going to end up over here somewhere. So we want to figure out this delta x when the time is 1.25 seconds. Okay, well, it turns out this equation will give us the direct answer, right? Delta x equals v naught x delta t plus 1/2 ax delta t squared. We have all of this information, right? So we can just plug in here. This is 30. This is 1.25. The acceleration was negative 0.50, 1.25 squared. And if you work this out, this is going to be 37.1 meters. So since the puck went further than the edge of the goal, right, which was 37 meters, then the Flyers did score, right? So the Flyers will win by 2. Goal is scored. Flyers win by 2 points. Okay, so we had to see that this is greater than the distance that the puck was away from the front edge of the goal. And that's true, so they must have scored. Okay, now how do we figure out the velocity of the puck just as it crosses the goal line? Because if it went 37.1 meters, right, it's already into the goal. How do we figure out the velocity right at the goal line? Well, to do that, we need to figure out the time that the puck crossed the goal line, which is probably slightly less than 1.25 seconds, right? Because we know it went 37.1 meters in 1.25 seconds. So it must have went 37 meters in slightly less time. So in order to answer question part B, we need to find the time first. Find time puck crosses goal line. And to do that, we can again use this equation. But now we're going to consider our unknown to be delta t, right? So now we know the displacement right to the edge of the goal line is 37. We know the initial velocity was 30. We don't know delta t. We know the acceleration is negative 0.5. Okay, so this now, if you look at this, see how you have delta t and delta t squared? This is a quadratic equation here. So you need to solve this quadratic equation. Here, I'll rewrite it slightly. Let me do, so if I do 1/2 times, so 1/2 times negative 0.5, that's going to be negative 0.25. So this is like 37 equals 30 delta t minus 0.25 delta t squared. Then I'm going to bring the delta t squared to the left-hand side. So I'm going to write this as 0.25 delta t squared minus 30 delta t plus 37 is equal to 0, right? So how do we solve this? Well, we can use, there's a couple ways. You could get your calculator to do it, right? If it's set up to solve a quadratic equation, you could use quadratic formula. However you want to do it, you want to solve this. Okay, so for example, you can solve using the quadratic formula. Where in this case, oh, I don't have any space in the bottom, so I'm going to go to the right here. In this case, remember the quadratic formula? If you have ax squared plus bx plus c is equal to 0, then x is going to be minus b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, our a is 0.25, our b is negative 30, and our c is 37, right? So you could plug that in and solve for our x in this case is delta t, right? And you're going to find that delta t is equal to 1.246 seconds, which makes sense, right? It's going to be slightly less than 1.25 seconds because it took 1.25 seconds to travel 37.1 meters. And now we just want to know how long it takes to travel 37 meters, which is slightly less time. Okay, so make sure you're able to get that. Again, I would learn how to use your calculator. It's much easier to do it than to use quadratic formula. Once you have that, then to find the velocity as it crosses the goal line, we can just use this equation now. So the final velocity as it crosses the goal line, is equal to the initial velocity plus ax delta t. And now the delta t I want to use is the time it took just to get to the goal line, right? Which is at 1.246. So this is going to be 30. That was the initial speed of the puck. Acceleration was still negative 0.5. And now the time is 1.246. And if you work that out, you're going to get 29.4 meters per second. And notice, actually, this makes sense too, right? Remember, it left the Flyers stick at 30 meters per second. And it's being slowed down a little bit by the friction between the puck and the ice. So it should be traveling slightly slower, right, when it crosses the goal line. And we're finding it just slightly slower, around 29.4 meters per second. Okay, and then last question. So one more example here. So you're told Brian is attempting to high jump over a crossbar set at 2.44 meters, same as 8 feet, but we're going to do everything in SI units. At the instant of takeoff, when he's no longer in contact with the ground, right? So after, just when his toes like leave the ground, is the way to think about it. His vertical velocity is 4.0 meters per second. So V naught Y is going to be 4, right? Initial velocity in Y direction is 4 meters per second. And his center of gravity is 1.2 meters high, right? So that's how high relative to the ground his center of gravity or center of mass is. In this case, if we're going to consider the athlete as Brian as and one single object, we have to kind of track the motion of his center of mass, okay? So the question is, what is Brian's vertical acceleration at the instant of takeoff? Well, in this case, Brian is undergoing free rise, free fall motion, right? The only force that's influencing Brian is gravity. We're ignoring air resistance. We're not taking into account the force that the ground exerted on Brian to allow him to jump, because we only care about the way this question is worded. We only care about when Brian's in the air, after he leaves the ground, right? And when he's in the air. So part A, it's kind of a trick. It's not really a trick question, but the vertical acceleration is simply going to be minus g, right? Because Brian is acting as an object that's in free rise, free fall motion. So AY in this case is simply going to be minus g, right? Or minus 9.8 meters per second squared at takeoff, right? Just after his feet leave the ground, the only force acting on Brian is gravity. So the acceleration is negative 9.8. Okay, what about the second part of the question? How much time elapses after takeoff until Brian reaches his peak height? Well, remember, at the peak height, right, Brian's velocity is going to be 0, right? So the final velocity is going to be 0. The initial velocity, and really you can think of it as the velocity of his center of mass, was given as 4. We know g is 9.8, right? And the negative is already built into the equation. And we're looking for delta t, looking for the time that it takes to reach the peak height. So actually, I can just use this equation, right? I know that Vy equals V naught Y minus G delta T. And then if I solve this for delta T, so I'll subtract V naught Y from both sides, I'm going to get Vy minus V naught y equals minus G delta T. I'll divide by minus G. So this will cancel. So delta T is equal to Vy minus V naught y over minus G. And then if I plug in here, right, this is going to be, I guess, 0 minus 4 divided by minus 9.8. And if you work this out, let me just double check it on my calculator here. I think it's like 0.4 seconds. So negative 4 divided by 9.8 divided by negative 9.8 is 0.40. Yeah. So 0.408 seconds. You could probably round it and say 0.41 seconds. Depends on how many sig figs we're expecting to use here. I'll just leave it as 0.408 for now. Okay, and then the last question is, what peak height does Brian's center of gravity achieve? Well, we can find the change in height by using this equation, right? We can find the displacement because we know the initial velocity, we know the time that it takes to reach peak height. So now if I plug this in here, right, this is going to be 4. This is going to be 0.408 for the time, minus 1/2. G is 9.8, and then 0.408 squared. And if you work that out, delta y is equal to, it looks like 0.816 meters. Okay, so that's like the change in height. Now you got to think about like what's going on here. If this is, I'll just do a stick figure, right? This is Brian. This is just when he leaves the ground. His center of mass is, say, right here. I'll do it in red. Let's say it's right here. And this height right now, what was it? It was 1.25 meters, right, above the ground. And then Brian jumps up. And we know that the change, the displacement in the y position, right, the change in position was so this distance from here to where center mass was when he left, this is 0.816. So if we want to find the total height above the ground, so this height above the ground, then I have to add the 1.25 to the 0.816. Does that make sense? Another way to think about this is I could say that, remember, the change in y, this is like y final minus y initial is equal to 0.816. And you could say his y initial is that 1.25, and the y final is going to be the total height from the ground. So then again, if you rearrange this, that means the y final is going to be equal to the y initial plus 0.816, right? It's going to be y initial plus delta y. So if you work this out, this is 1.25 plus 0.816, and that's going to equal 2.07 meters. So this will be 2.07 meters. So that's the y final here, 2.07 meters. Right, that's the total height that his center of mass is going to be above the ground. If it started at 1.25 and we calculated this delta y here, this is like the delta y is 0.816, then the final y must be 2.07, must be the sum of those two. Okay, again, like anything else, this is going to take some practice. But the nice thing here is we're only dealing with constant accelerated motion, right? The acceleration is constant. Great, thanks.